Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. It's my pleasure to introduce Professor Chen Ding. Chen is a professor at the University of Rochester. He just got tenure, so congratulations. And Chen has worked a long time on data locality and some of the other stuff that I've been working on, so I followed his research pretty closely. And he's also done some exciting work on program phases and understanding program behaviors. So he's going to talk a little bit about his latest research. So, Chen?
Very good to be here, and thanks for the introduction. And I always remember this first computer in 1987 was a Macintosh, but the first programming system I used was Microsoft Basic. I spent a long time writing basic programs, and the foundation of my English reading was actually the I think a 400-page manual. And just very quickly talk about the department of computer science at Rochester. Is a small department and specializing in 3 areas. Used to just produce PhD, and just recently I did a bachelor program. And my colleagues, and many of them you probably already know. In fact, Michael Scott was here giving a talk in the summer. He and your alum, John Miller-Cromie, so their earlier work served to launch the field of scalable synchronization. John Miller-Cromie is the program chair for this year's PPOP conference, and he and Michael just received this year's Destra Award in distributed computing for their influential work. And so I look at programming systems, and the joy of being a professor is to ask the talented young students the basic question: what is a computer program? And at Rochester, they actually go through this series of courses. First, they learn the programming language constructs using the book written by Michael Scott, and then they come to the advanced programming systems class, where we teach them that programming is not just a set of statements, but actually has control and data flows, and you can derive invariances. And then if you want to transform, reorder these statements, there's something called dependence you need to understand. And all of this would be redundant here. So let me move forward to introduce the topic of my research is program behavior. It's increasingly difficult to figure out what the program will do by looking at the code. It's really because the relentless push for software reuse. So we have same code, multiple data. In fact, that's how we get segmentation fault. And then we have parameterized code. It's the same name, different functions. And then nowadays, when we run interpreted programs, most of the code actually not inside the program, they're outside. But when we look at what the program does, it's a complex composition of all these factors. And the definition of program behavior in my version is a long sequence of operations. And I emphasize the word long because modern processors every second can execute up to billions of instructions. And then this sequence of operations changes with the input and with the environment. So what we have been doing, and along with many others, I think Tricia and I are birds of the same feather. We really look at, in addition to program code, we want to understand by looking at the program behavior, by looking at the traces. The basic metric in behavior analysis that we do, it's called the reuse distance. So given a trace for each memory access, the reuse distance is the volume of data between this and the previous access to the same data. And it was first defined by Matheson and others at IBM in 1970. And then if I take the distribution of all the length of all reuse distances, so I call the histogram reuse signature. So for example, given this trace, the reuse distance of the second B is 2 because 2 distinct data elements are accessed between the previous access B and the current one. And if I measure the reuse distance for every memory access, and then if I take the distribution as a histogram, so this is a distribution of all finite length distances. We see that 50% of reuses have a reuse distance of 2. And so half of the actions have actually use 2/3 of the data. And let me say a little bit more about this basic metric, which I'll use again and again. It's really a measure of behavior. So it's not a measure of coding styles. For example, I may allocate data at different places. I may unroll a loop, but this will not change the reuse distance. And also, it's independent of hardware effects. And also, it's because it's cumulative, the small-scale perturbations do not matter. And it's a measure of memory performance because it contains both frequency information and also volume information in the sense that's the working set between the repeated uses of the same data. And then at the practical level, it predicts the miss rate of different cache sizes and actually different cache configurations. And so it's really the equivalent of the spectrogram, a spectrum. And behavior analysis, one of the goals is to identify components at the behavior level. So instead of looking at the code, look at the function calls or variables, we like to look at the cumulative behavior, identify components and patterns, and then we will map the behavior back to code and data. And so professionally, I consider myself a scientist and a good programmer, and also increasingly an educator. So a question I care a lot about is whether what I do is science. So I first draw some tongue-in-cheek analogies before showing some more serious stuff. So Rusford once commented that in science there is only physics. Everything else is stamp collecting. And now you see physicists comparing the universe as the computer. Basically, it's the physical laws are the program. And that's running the universe. So in that sense, physics is program analysis. We're analyzing this one particular program. Look at the behavior of the universe, try to derive this one program. And biologists used to analyze only the behavior, but now they have the code. And it's a very interesting question they're addressing, that why, for example, chimpanzee and the human share so much code, yet we're so different in behavior. So in that sense, it's also behavior analysis. And early days of the internet, the problem is often formulated as a graph problem, the topology of the web. And I remember telling John Klimberg at the time that really what's interesting is when people start to use the internet. So what's the usage pattern? And nowadays, I saw an article that Yahoo search analyzes 10 terabytes of clickstream data every day. In our analysis, a program actually can generate that much data in a few hours if we analyze the full trace. So a lot of the behavior analysis problems are actually related. And so now I'm going to talk about what we can really do with programs. And the basic components I'll talk about. One is the whole program locality. So really the question, how much data does a program use? And then I'll talk about the finite patterns in different dimensions. So whole program locality is a global average, and then we'll subdivide in space and talk about the reference affinities, the relation among data, and then the subdivision in time, locality phases, and then we'll talk about what we can use from these behavior patterns. And due to the lack of time, we only show the surface without the body in most cases, but we have time either today, tomorrow, after I come here to flesh them out if you're interested. So first I want to show you the reuse signature of a real application from NASA. This is a full benchmark that computes fluid dynamics. And being NASA, you probably can imagine why they care about fluid dynamics. And I used two fairly small input sets. And for the first one, I'm showing the reuse signature as a line drawing, just for ease of viewing. And the legend shows the length of the execution. Class A input has 23 million accesses. Class B has 2.3 billion memory accesses. If I let you to look at these two traces, probably the chances are you won't find any relation between these two executions. But looking at the reuse signature of Class A and then Class B, we see a striking similarity at the early part. Even at the latter part, you see that the shape is, the volume is actually similar. It's just the distance has been lengthened in the larger input. And the peak to the right of the spectrum are the ones that cause cache misses. And we see here that 1/3 of memory references have inherently long reuse distances.
Are you measuring single word accesses?
Single data elements. So these,
like an element of an array.
Right, each distinct address is treated as a single data element. So it'll be 8 bytes data in this program.
So some of it might be prefetched because it's already in the same cache line, right?
Right. So the actual cache miss rate would be, in the perfect spatial locality case, would be reduced by a factor equal to the cache size. And that's actually a distinction between the reuse analysis at the program level, at the cache level, at the OS level.
How big is your second level cache? Because it looks like Class A would fit in a serious second level cache.
Yes, exactly. That's what the reuse signature can show. Given any cache size, it can estimate what's the miss rate. But we see that if the data size increases, any fixed size cache won't be able to hold these reuses. And this is actually a serious problem. And to show these, so I already mentioned these two, to see why this is a problem, and let's look at the concept of program-machine balance. The program SP that I showed in the previous picture has a program balance of 4.9. That means for every operation, this program needs about 5 bytes of data from memory. So 4.9 bytes per operation. That's the demand of the program. And then here shows the machine balance, which is the supply. So at the peak performance, the machine at the time, this SGI machine, can supply 0.8 byte per operation. And compare demand and supply, we see that it's a factor of 6 difference. So because of the cache misses and the insufficient bandwidth, this program at most can have 16% of CPU utilization on average. So just because of the bandwidth constraint, it's a fundamental constraint. And this is a table I used to start my dissertation work. We see that the bandwidth is not enough for all the programs But there is one exception in this bleak picture, which is matrix multiply. Without optimization, it's memory bound, but after optimization, we see the compiler actually reduce the memory demand to be so low that its bandwidth is no longer a bottleneck. So, and this observation actually led to an interesting excursion in architecture class that I took from Steve Wallach in 1999. So at the time, people always talk about designing next generation machines by putting more CPUs on chip. But the problem we see is that because of the insufficient bandwidth, the maximal utilization of a single CPU is only 16%. What's the use of having 10 other CPUs? And so instead, I proposed a design, say, let's not worry about CPU. The current one is pretty fast. Let's just concentrate on the interconnection to build a really high bandwidth connection between memory and the CPU using crossbar.
But Chen, isn't one problem is you're limited by the number of pins you have on the CPU too? It doesn't matter what you're interconnected. There's so many pins that you can only push. It's a packaging problem.
Mm-hmm. Right. So 2002, here is a solution from Earth Simulator. This picture shows the interconnection network. These are the processing units, so 640 of them. And these are the memory modules. And there is all-to-all connection through 83,000 cables. And each cable is 12 gigabytes per second bi-direction bandwidth. And you can imagine the cross-section bandwidth on this system. And it came as a surprise because at the time, the fastest American supercomputer can do 7.2 billion operations per second for LINPACK benchmark. And this machine was 5 times as fast. So that was a huge embarrassment to United States leadership. And this machine at the time was as powerful as the next 12 fastest supercomputers in the world put together. And so when I heard the news, I knew it happening. This could be done. Really, the reason that this machine has 5 times performance as the American supercomputer is not because it has higher peak performance. It just has the higher sustained performance because of the interconnection. Now, the LINPACK benchmark actually is matrix multiply. So remember the previous figure, the only program that we know how to reduce bandwidth demand was matrix multiplies. So 2005, IBM Blue Gene L overtook Earth Simulator, so achieved the sustained performance, I think the 4 times the Earth Simulator. But this machine is extremely difficult to program, in part because the data communication. And in the sense that really whether the Earth Simulator is the right direction or the Blue Gene L is the right direction depends on the program. How much memory transfer does the program inherently needs? And this is the results from my early work. Again, I'm showing you the real signature for the Class B input. Right? It's a huge peak. And if we cannot reduce the size of this peak, then Earth Simulator is the right architecture because it's really memory bound. But if we can reduce this peak, as we did for matrix multiply, then Blue Gene L is actually much cheaper and faster. So we did heuristic-based methods to study the potential. And so it's physically possible to lower the bandwidth demand as shown by the resignature. And then the particular program transformation, reuse-based fusion developed by my thesis work, getting sort of pretty close to that potential. And so this is the result for this one particular program. And in general, loop fusion is actually NP-hard problem for minimizing the bandwidth demand of a program. And also, loop fusion doesn't, because depends on dependence analysis, it cannot, it's not very effective on integer code. And the state of art today are the manual transformations. People do at least 2 groups that's published results recently to fuse the computation so that we have as few long-distance reuses as possible. And to help this, part of a work I did in 2004 is to have an automatic tool to automatically measure what's the potential before programmer starts to transform the code. It's actually very difficult to transform the code, and really the limit to which we can reduce the bandwidth demand is very much an open question. But one theme actually we'll come back to is that through these studies, we actually see that programmers can make very creative transformation. It can quickly identify the key parts in a large application that has memory performance problem and make very creative transformations. But programmers do not have the complete view of the program.
Wait, I didn't understand that last comment. You said that they could make good transformations, but they don't have a complete view?
In the sense that they take a function, they see there is a problem, then transform it. But they use data used by other part of the programs too. So one, they don't know how intensive are the uses elsewhere. Second, they don't know whether the transformation will positively or negatively affect things elsewhere. And even just for correctness, by changing, for example, the function call, the other function calls, it may be correct for a few runs, but it's hard to guarantee that's always correct. Yes?
Can you say a few words on this study of the potential? I mean, how do you take an analysis of a program and a priori decide how much you're going to be able to help?
Right, the problem is an NP-hard problem, and that's the same reduction that did here. And what we did is sort of greedy heuristic. So the Bilardi strategy, right, the optimal data cache management, is to say, if I don't have enough space, I replace the data that I'm going to use the furthest. And the heuristic to reduce the reuse distance is to say, I'm currently using data X. Now the next operation I'm going to do is the operation that again uses the same data. So it's sort of we group the computation on the same data. That's the heuristic being done at the trace level. So it's a potential. It's reachable, but it's not clear what's the right program transformation to reach that potential.
You're basically taking a trace and running an oracle.
Right. It's sort of applying Bilardi strategy, but in a different way. It's for managing the reuse distance, not the cache. And next, I'm going to show you the result for integer code. So we thought these are complex programs, and we're curious about what patterns we would see. And this is GCC compiler compiling program files that's made up of GCC. And what surprised us is that despite these different inputs, they use 500,000 data to 1.5 million data and access them 22 million times to 134 million times, but the reuse signature are 98% identical. And so that's one observation, that they have extremely similar reuse behavior. And second, the reach distance is bounded, so it's the maximum only reached to 512,000, and it's a very small amount. So what this says is that a large cache would work very well for this program. So basically, with a large cache, I won't have a memory bandwidth problem for GCC. And I remember John Hennessy once gave a talk that he marveled that over the years, we improved spec integer performance faster than we did with floating point benchmarks. I think one reason is because integer programs have much better locality. As a result, it's not constrained by the memory bandwidth bottleneck as much as we have. Yeah.
Was GCC doing extensive interprocedural optimization?
Somewhat. I think this is spec 2000.
I just noting that if you do interprocedural optimization, we have to look at the whole program. It's not clear that this result holds up.
Possibly. I should double check, but I believe this one does inlining. And the other reason that the real signature are similar, I think, is because it has this abstract syntax tree. When it operates on a tree, most references will be sort of at the top of the tree instead of the leaf of the tree. So on average, you still have most references have short distance reuses. So same thing is observed in sort of tree search type of programs. And then I mentioned that the resignature actually independent of the data allocation and particular control flow. So we can compare the behavior from different inputs. And next, let me show that we can also compare different programs. So does this resignature looks familiar? And it's the real signature of latex. And it's a typesetting and formatting system designed by News. Let me show you GCC again. Okay. So why would latex have a similar behavior with GCC? I don't think their development team overlap at all. Very different applications looking from the code. Guy Steele's comment was that News didn't start latex with the realization that he was designing a programming language. Okay? And that's, it's indeed true. Really, the typesetting is just another language, and the latex is actually the compiler for that language. So this similar behavior actually shows that there is really a substance in Guy Steele's criticism. It's because I think this is possibly showing a compiler pattern in the reuse behavior. And
is there any reason why around 16 you get the peak?
That's a good question. I suspect it's something to do with the abstract syntax tree. 16 is that, I don't know.
Have you tried with something other than LaTeX and GCC?
We tried PostScript, which is another language, and it doesn't show similar pattern. But PostScript is actually an interpreter, not a compiler.
Result independent of where the objects are, I guess.
Yeah.
So it's every address is treated independently.
And so it's a sort of computational study. There is no reason why they have to be this way. Just from the observation, seem to be an emergent pattern. And next, I'm going to move on to scientific program again, because they don't have the same real signature, so the problem is a little bit more interesting. And here we're going to do a component analysis on the spectrum. And the goal is to separate out these different components and then make predictions. So there are this is Lucas programs from Spec 2000 is testing the primality of large numbers. I'm showing you two training inputs. This is the reuse signature for the small one, and then reuse signature for the medium one. And the component-based analysis will analyze and see that this part will stay the same distance, but this component will move as the input size changes. And it will build a model to predict the reuse signature for a new input. So let me show you the third input in the spec benchmark set. And it's if you look at the length of the execution and the legend, it's 3 orders of magnitude larger than the 2 small ones. But the model built from the small training runs was able to predict the reuse distance of the large run up 94% accurate. And we see that the 2 reuse signature match pretty closely. And this just is a very good example showing that behavior-based analysis can predict the memory behavior based on analysis of inputs that's 3 orders of magnitude smaller.
So is this your best case or average case?
94 is average, although GCC it's sort of a cheating because it's so easy to predict.
So what model are you using for prediction?
Oh, I can tell you after the talk. So divide this into small components, 0.1%, and then we try to build a formula for each 0.1% of memory references. And then with there is a parameter so you can view it as the size of the program data, and then that's a parameter to predict how that 0.1% will change. Here it will not change reuse distance, but here it will change. And with this, we can define whole program locality quantitatively as the miss rate across not just all cache sizes, but also all inputs. And the z-axis here shows the miss rate, and x-axis shows the cache size, and y-axis hidden behind the surface is the size of the input measured by the number of cache blocks touched by the execution. And we see that behavior not as numbers, but shapes, plateaus, and the valleys. And so really the scale of things matters. A stone does not make a plateau. A raindrop does not make a storm. If we want to improve the memory behavior, we have to change the shape of this surface. And next, I'm going to show you the effect of loop fusion. And not only to reduce the cache miss rate overall, but you see that it also changed the shape of the locality. And visually, the art of locality optimization is the art of moving a mountain. Right. Now, with this overall reuse signature, it's just an average, so there is no structure yet. And next, I'm going to show you the analysis that first a subdivision in data dimension to look at how data are related in their usage. And motivated by the fact that memory hierarchy is organized as blocks. And it's actually out of a necessity, the latency of loading a data element from different levels changes from bad to unbearable, taking data from disk takes millions of cycles. And really the trick to amortize that cost is to use large blocks. But then we have a utilization problem. Really the performance depends on how well we utilize the block. And the basic problem is what data are used together. And the analogy of this problem is the Amazon's recommender system. If online shopper buy book A, then what other books that online shopper may also want? In the program behavior analysis, if program loads data A, what other data are going to be used? Except here we're dealing with a much larger scale. We want to predict preferably next millions of data elements that the program may want to use. And some of the best known pioneering work for this problem is done by Ben Brad in 2 papers in ACE Plus 98, and Tricia and Jim in PODI 99. And it was actually one of the times that Tricia had 2 PODI papers. And here we're looking at the static placement problem. And in the notion we call reference affinity, actually coined by Ken Kennedy. So we say a group of data have reference affinity if they're always accessed together. So just very quickly show you the mathematical properties of reference affinity through this example. We model the closeness of the affinity by hierarchy. And the parameter is really the quantitative definition of this closeness. At the top of the hierarchy, when I'll say closeness K is infinite, then everything is close to everything else. The whole data set are in the same affinity group. And if we reduce K to 3, we see that W, X, Y, Z are accessed closer with each other than they are with U and V. And by further reducing K, I see there are substructures in the first group. And the bottom of the hierarchy is when K is 0, the no 2 data elements are close. So we have each single element in its own group. It's a beautiful system, has very nice properties, but then we need to test whether this has anything to do with reality. And turns out there is a very good test, which is structure splitting and array regrouping. Which a problem, structure splitting was first studied by Tricia and Jim. And at the same time, we actually studied array regrouping is the really different faces of the same coin. So given the object with, say, 7 fields, there are actually over 200 possible layouts. Okay, depending on what are used together, we may want to pick one from them. And the program that has most attributes is a scientific code called SWIM, doing shallow water simulation. It has 14 attributes, so that means 6 million possible layouts. And and then in addition to the choices, we have different platforms and compilers, and then that's Aris and his co-authors result that optimal static data layout is unreachable if P is not NP, and worse than that, the optimal layout cannot be approximated by a constant factor. And however, with the reference affinity analysis, the affinity-based layout, when compared against 7 other methods, including statistical clustering, the original layout given by the programmer, and the frequency-based method, the affinity-based layout ties or wins 97% of all cases and never loses by more than 1%, or a small fraction of a second. And the larger structure, the more attributes the program have, the higher the improvement. And SWIM is really illustrative in this result. This is the reference affinity hierarchy identified by the analysis. We see that CV and Z are accessed closest, and then then H and CU, and then the 4 are closer together than they are with others. And the y-axis, which is the closeness, actually has direct interpretation in terms of the cache size. So knowing the cache size is just a matter of making the cut at the right place to to regroup these attributes. And it outperformed the carefully tuned optimization by the IBM compiler, which surprised the IBM group at Toronto. And you can see why hand tuning is not very effective on this program. It's just too many choices. And with the model of reference affinity, we can actually see the structure. So analogy that the components, knowing the components is not enough. We need to know the structure. Just a collection of components is no more than a good system. Then a heap of stones is a house. And the other interesting anecdote was that the IBM invited my student to go there and implemented this a compiler version of this analysis. And it produced a different reference, it's a different affinity hierarchy than the trace-based analysis on the same program, on the same machine. So, and it puzzled us for a while because and eventually we figured out that because the trace-based analysis was analyzing the binary code, which is after compiler optimization. And the behavior is different before and after the IBM compiler optimization. So as a result, the trace-based affinity hierarchy performed not very good for the unoptimized swim program. But once it's fully optimized, it's actually better than the compiler analysis. The compiler produced the affinity hierarchy.
You could just as well use a trace from the unoptimized version. That would perform well.
Right. So if the optimization changes the behavior, then that change needs to be taken into account. And we see the benefit of behavior analysis actually taking into account the effect of the compiler. So this is a trace-based hierarchical model, and we did a careful theoretical study and improved the analysis method, mostly done by my student Chengliang Zhang. And part of that work shows that it can actually identify hierarchical data placement for the common type of recursive computations in matrix operations, wavelets, and n-body simulation. And then the work with the IBM compiler shows that the trace-based models actually can be useful for compiler design.
Did you try this for GCC? The reference affinity hierarchies, or the structures are not big enough for?
But it's not clear which structure to analyze. We didn't try. Part of it because the infrastructure we had couldn't instrument GCC at the time. We needed source level information because we know a particular memory reference is accessing which attribute of an object. So next I'm going to move from space to time.
I have this question on affinity. The definition of affinity as you take.
Mm-hmm.
Is it like a strict always clause there?
In the-
sort of relaxed in the sense that if two data element has to have affinity with a particular distance, you consider it if they are always having that kind of distance. They are always access together with that distance.
Right, in strict reference affinity that's required, so it always access together. Although the closeness also depends on the size of the group. If the group has a lot of elements, then they may appear at different order. It's a pretty somewhat involved definition we can discuss offline.
But actually, to take that question a little further, so it doesn't take into account the fact that the program has phases, right? And that two elements might have affinity in one phase and not in another, for example.
Right. So this has to be the property hold for the entire trace. Right now, thanks for the question. It's an excellent lead. Once we have phases, we can analyze reference affinity interfaces.
I think the way you are doing it, you are collecting some runs, statistic based on some runs. the trace could be for some runs, not for all the runs of the program. So
we can collect trace for all memory references.
yeah, but for some particular runs of the programs.
Right. When we decide on the affinity between attributes, we really take the access of different attributes separately and compare the reuse signature. And there is no good commonly accepted definition of phases. We define the program behavior phases. So it's a unit of runtime behavior and marked by program points. And we try to, through phase analysis, to help analyze input-dependent behavior in scientific simulations and the utility and the service-oriented programs. And we use two types of analysis. The first is uses reuse distance as a signal. So here it's a trace. Each memory reference is a logical time, and then here the y-axis shows the reuse distance, and here we ignored the short distance reuses, so the points here are not shown. And it's a reuse distance turns out to be a very good signal because there is one number associated with every element in the trace, as opposed to cache miss rate. It has to be averaged across a window. Then one has to decide the size of the window as an arbitrary parameter. And what this signal shows is that the behavior changes all the time. And our definition of phase is the point of disruptive changes. So we see that the behavior changes gradually here, but then there seems to be a disruptive change. The pattern shifts. And we use the wavelet analysis to identify these points of disruptive changes. And in this year's PACT, there are two new papers from other researchers look at the other aspects of wavelet analysis, sort of a multi-resolution modeling of the complexity of the program behavior. And the other thing we did is to find hierarchical phases, because you see some of the phases repeat as a group, and the technique we use the same as Jim and Tricia used is the grammar compression based on sequitur. And this was a problem for our analysis. So this is not reuse distance, actually the speed measured by the hardware counters, IPC, over time. Do you see phases, repeating behavior in this execution? They go up or down, right? One of the two directions.
There's that sort of white group there that repeats itself 3 times.
Which one? This one?
Yeah.
Okay.
There, and then it's compressed earlier. And then
That's very good. And so wavelet analysis couldn't deal with this complex graph, and we came up with a method we call active profiling. So it's complex really because the behavior is input dependent. It's compiling a series of functions in the input file. The functions could be large or small, and we can turn this problem into a feature. So we can construct a simple input, so just a file containing 5 identical simple functions, and then feed that into GCC. And then we induce a regularly repetitive behavior. Then the problem is so simple, we don't even need wavelets. So this is Shippon's analysis that finds the outer phase, which is the compilation of each function, and then the subphases, 8 subphases in large code. And after that, we see that as Ben observed, these are subphases of compiling a large function. And then we see another fairly large one here. And if I magnify it, you see actually the different subphases have similar behaviors.
So are code markers the right way to mark in phases?
So how do we pick the markers?
I mean, is it the right abstraction for marking phase boundaries? Code markers. I mean, I don't know.
Well, with code markers, the nice thing is that after offline analysis, when the program runs, it will self-announce the phases. So by marking the code, you do one analysis, then every time it runs, it gives out the phase information.
In which the code is called manually.
Right. So the analysis actually a little bit more complex. We use regular input to identify potential markers. So if there are, say, 5 regular functions in the input file, then the potential markers are basic blocks that execute 5 times. And then we also look at the distance between this recurrence of these 5 blocks to make sure they are evenly separated. So after this filtering, this 2-step filtering, we have a third step. We'll pass in an irregular input and then further filter out the markers that are false positive. So markers depends on the context will be hopefully filtered out.
So how do you define the context?
So any marker that doesn't consistently mark the phase behavior in the controlled test. Because in the controlled test environment, we know what are the phases. At least we know the frequency of the phases. So any markers that do not give that information, then is filtered out.
So all the markers, I guess, have no context. It's just the static code point.
Right.
And that could miss quite a few. That could also miss a lot of points where you would otherwise be eating phases. Here, because you're looking for common, you're basically trying to see static.
Right. If there is a consistent association between a code block and the phase, we will find it. But it's possible that same phase actually need to be identified, cannot be identified by a single block.
So, I mean, an example would be if I do a tree traversal, right, and it's recursively defined, the first time I enter the traversal, I'd like to think of that as, the beginning, the boundary of a phase. But if it's recursive, I'll see many recursive invocations which won't have the same property as the initial top level. So would your analysis throw that out as an entry point, as a starting point?
Right. If I view the number of times I traverse a tree as the frequency of the phases, then these blocks executed in the recursive function traversing the tree will be filtered out because they have higher frequency. Right. But very likely it will find the call site that you call this tree traversal.
So it'll be the call before the first recursive call.
Right. So you actually look at all the code blocks, and if there is one that correlates with the phase behavior, it will find it.
So I guess the real question is then, how many times do you miss something because you can't find this consistent code? Right. If you use the context of, well, this code block, when it's called from here, how many times do you get additional phases that are not subsumed by, well, this is also kind of encapsulated by using a static code block somewhere else?
Right. Yeah. So we're looking for a simple correlation. No, this is that's hard to verify. That's a large piece of code, and so this is the type of verification we do.
So, I mean, there's only 8 phase markers, right? So what are the phases correspond to?
One of them is a loop optimization. And one of them, I think 2 of them are 2 stages of register allocation.
Okay. But isn't GCC compiling a file that has many different functions in it?
Right.
So wouldn't it go through the phases?
Repeatedly. So you probably can't see the solid vertical lines are the phase, outer phase. That's each instance is compilation of one function. The dotted lines are subphases when compiling a single function. Okay. So next, move on to some of the optimizations, adaptations we do with behavior analysis, and this is Chen Liang's recent work in ICMM. In traditional applications, enough memory is enough, but for garbage-collected programs, giving more memory may improve performance because it reduces the frequency of garbage collection. And he developed a simple behavior-based control. So it basically keep using more memory until the memory is exhausted. Then how to predict how much memory the system has? It rather than making prediction, it's doing a simple reaction So on Linux, there is a proc file system will constantly record how many page faults incurred in the last time period. So if it starts paging, this control loop will start to reduce the heap size. And it's at program levels, there's no VM and OS changes. And the extension of this, which I'll describe in 2 slides, is a program sponsored by the Phoenix Router program. So this shows it's really the simple reactive scheme. It's really effective. We take a machine with 128 megabytes of physical memory and run spec JBB on IBM JAX RVM, and then we fix the heap size program to use different heap sizes from less than 50 megabytes up to 260, and then we measure the running time when it use 3 different garbage collectors. So here we see that the performance changes based on different heap sizes and also based on different garbage collectors. So this is an excellent example showing that the behavior of the program actually doesn't depend on the program itself, but depends on the virtual machine, so which garbage collector is being used. And the adaptive scheme will adaptively find the sweet spot, so the best spot, best heap size for the given garbage collector. The bottom 3 lines shows the performance using this simple adaptation scheme. And it doesn't depend on the specification of fixed heap size because it doesn't use that information. And then recently, we look at the running these programs, GC-based programs, in a shared environment, and this found a very interesting problem because the sharing of the CPU is relatively straightforward. For throughput, if I have 5 processors, it doesn't improve my throughput if I run more than 5 programs on them, if the programs do not have I/O. But for memory, it's possible. If we don't have enough memory, running them in parallel actually hurts performance. So here is an example. On a dual processor machine, we run 2 copies of spec JBB with generational mark sweep collector. And the throughput is the total running time when the 2 finishes, 2 copies of JBB finish. And this is the running them sequentially. So they don't share memory because the 2 copies are run sequentially. And then if we share the memory, depending on how much memory we have to share, if it's here, we see that the parallel execution actually is a lot slower in terms of throughput. And then at this point, we have enough memory to share to actually benefit from parallel execution in terms of the throughput. This shows the default fixed heap size scheme. And the other 2 shows the adaptive scheme, one selfish, one cooperative, that I don't have time to explain. So it's very interesting because with adaptation, each copy will try to use more memory. So these are not sort of benign and friendly as dolphins. They're actually sharks. They keep grabbing memory. And then here shows how so if we throw 2 sharks in a tank, what happens? And it turns out that we have responsiveness, fairness results too. And it turns out that sometimes, although cooperation helps the throughput, in terms of fairness and the responsiveness and also the consistency of the result, the selfish PEM actually it's more consistent. It's consistently good. So that maybe in praise of capitalism. And then the other thing we did very interestingly is to build a model to predict the crossover point. So we want to be able to predict at how much memory do a parallel system need. So it's it's concept called time memory curve. Basically, given a physical amount of memory, what would be the execution time? And then using this time memory curve, I hope you can see this very faint line. That's the prediction of the parallel performance. And we see that the cross point happens here. That's about between 250 megabytes and 300 megabytes. So that shows that if you have this much physical memory, then the parallel execution will have better throughput. And indeed, that conforms from the crossover point in the real measurement. So again, this is a work by Chen Liang. Okay. And how much more time do I have?
You should wrap up pretty
Okay.
soon.
So the last part is something I actually did a lot of coding to implement this system. It's what we call behavior-oriented parallelization. So high-level parallelism exists in a lot of programs, but parallelization is hard because of all these problems. And programmers actually are very good at looking at part of the code and try creative solutions. So what we want to support through this, what the acronym BOP system is to support parallelization using partial information. So a user just looking at part of the source code can try to parallelize it, or a profiling tool examining a few inputs, again, based on the partial information to parallelize it. And this, there is a programmable interface called possibly parallel regions specified by a user or tool. And for example, in this loop, if the programmer intuitively know that after getting the work, this may be sequential, maybe coming from a queue, but this is parallel, then the programmer can put this, say this is the possibly parallel region. So that's the pipeline loop parallelism. For function parallelism, the programmer can say here is a PPR, and here is another one. And it uses general speculation support to ensure correctness. And this is a system that I really like because it allows a user to program the system. And let me show you the result, and then we can come back to this. It's the newest result we collected from a recently installed 4 dual-core Intel machine, so 8 CPUs total. And we were able, so through automatic techniques for these two and the manual changes, in addition to automatic support, the BOP support, we parallelized the Lisp interpreter, the gzip compression program, an English language parser, and also a scientific library. When speculation depth is 1, that means they're using 2 processors to process possibly parallel regions. So here 4 processors and 8 processors. And we see that this is a comparison with the fastest sequential implementation, and we get integer factor improvements.
You said there was general speculation support. So I guess what I'm missing here is how you make sure that this is actually correct. That you haven't parallelized programs and it works okay for 2 examples, but on the 4th one it breaks.
Right, you use processes. So at the beginning of the PPR, it forks a process to start from the end of the PPR. So if anything doesn't go as expected, we can simply kill the speculation. So it's really protecting the entire address space. And it has high overhead. So the PPR scheme is crucial because we need coarse grain tasks to hide that overhead.
How does data get transferred back from the process to the parent process?
So at the end of the parallel execution, they'll check for dependencies and they commit. And then there's actually a tournament is being run because we don't know whether parallel execution will finish correctly or finish fast enough. So there is a we call understudy branch. We'll redo the sequential execution, and so there is a competition between the two. So that's key to deal with dynamic parallelism. For interpreter, for example, a lot of those expressions are not parallel, but we have very little overhead by speculation. And then when there are expressions that are parallel, then we get benefit. And if the parallelism is not large enough, the understudy branch will finish first because it doesn't have the overhead. So again, it's a few tricks.
So to summarize, you have a machinery where you fork processes. You do something to figure out what data changed in the process of execution, put it back into the parent process. I'll ask you more about this offline. It's a coarse-grained parallelism.
Right.
Okay.
And it's one of the most interesting systems I think that we have built. In the past, there is no user interaction. And in my view, the end goal of my work is really to help people, not machine. And I quote Alan Kay's comment that he saw personal computing as an amplifier for human reach rather than programming system design. So I hope at the end I can say the same thing about program behavior analysis. I think Jim Loris echoed a similar view in the review of Michael Scott's book. You said the book shows that programming languages are the true center of computer science, bridging between people and systems. Now I get Jim's attention. So that's I have a few other things. And measuring reuse distance is not trivial. And if you're interested, so we have asymptotically the fastest measurement algorithm with guaranteed precision. And then there is a new paper by Shipeng, now a professor at William Mary in Papel, that approximation using time, although with not correctness guarantee, precision guarantee. A good literature survey is in the PODI 03 paper. It helps to people to rediscover a lot of several earlier work. And then there are many other uses of reuse distance. I've been talking to people about some of this. I will not go into details. But it seems that reuse distance is quickly becoming a versatile tool for behavior analysis as data flow dependence are for program analysis. And there is a really cool tool designed by a Belgium group that can, for program tuning. So I showed the reuse signatures, but it didn't really relate it back to program code in the way that they could. So for long distance reuses, actually break down into sections, and then they point out, for example, this blue part of the long distance reuses was caused by the reuse from here to here in the code. And then the part of the reason that I'm excited to come here for sabbatical is a chance of collaborating with Tricia and others. And what we have is most of our offline behavior models. And that's a really interesting contrast to the dynamic behavior models that Tricia had. So in the past, we sort of viewed the frequency of elements and pairs, and really this state of art is the stream model that looking at the sequences, the frequency of sequences, and these runtime low-cost profiling methods. And the other one is a stride pattern, another behavior level pattern studied by a number of groups. So finally, I want to show you hopefully a nice picture of where and when we work. And to summarize, in the research we had come up with structured models of large-scale behavior, and we found interesting emergent patterns. And then we found ways to link the behavior, so decompose it into components, and then link them back to input data and code. And so whole program locality links behavior, and input reference hierarchy links behavior with data structures, and phases links with behavior with temporal behavior with code, and then use this information for adaptation and for programming. So I want to acknowledge my collaborators and the generosity of funding resources, including Microsoft Research.
Right, that's fine.